Alright, so R is related to itself, and whenever this happens, we often say that X is R related to Y. That's one way of saying. We also often write a peculiar infix kind of a symbol like this. And when we do this, we usually have the strange formalism of denoting the relations by Greek letters so that we do not mix them up and so on. So we often say X row Y, so this is in that, if you write it in this way, so thinking that this same is row, then you will also write it as for all X in A, X row X. This is how often in most books, this is how reflexive relations are defined. And maybe as an exercise, it will be given that R is reflexive if and only if this happens, this condition happens. So what I have done is I have actually reversed the thing, the order so I have taken, well, there is a famous statement by a mathematician called Herstein. He said that old theorems get into definitions, make definitions. So, and since this is an if and only if, you can take any one of them, so it's perfectly right. Now, my reason for taking this one is completely different. We will see as we proceed throughout the course that although we started off with elements, we will be speaking in terms of elements again and again. So that's the whole point of set theory. But kind of we would try to always describe things in terms of relations and functions. And very soon we will get to know why we are doing this. Okay? So that's the reason. So one way to tackle this animal in definition 4.1.1 is to write it out in this in the language of elements, and then you will have a much more seemingly concrete picture. Seemingly, I'm saying, I don't know now which one is really concrete, but seemingly concrete picture, element-wise picture. So that's why I have in fact called that exercise 4.1.1 as element-wise descriptions. Yeah. Okay. So does this help a little bit?
It helps a lot. Thank you, Doctor.
Okay.
Yeah. I wanted to ask something about week 5 as well, but shall we first see if the others?
Yes. In any order, but yes. Anyone more with week 4? I just needed to tell something, but I think I'll tell it on I'll send a written note, so that would be easier to understand. Okay, yeah, on week 4, anyone else? Regarding the 4.1.2, let us try a few examples. So, okay. So then this was the scenario with reflexive. can you tell me what will be the scenario with symmetric? So it says R op is a subset of R. Okay? Now combine this with one of the previous exercises of week 3. Which one is it? It is 64, equation 64 and 69. So if you combine this, if you look into this, so this means, so let's see, R op, this implies R op is a subset of R, right? But this statement then says, sorry, a subset of R op, but this statement then says R is a subset of R op. So R op is a subset of R if and only if R is a subset of R op. So this therefore is same as saying R is equal to R op. So now do you see the meaning behind this symmetry? If it says so what does it mean therefore? It means that for all U, now extensionality comes in, U belongs to R if and only if U belongs to R op. Now if you, when does U belong to R? You mean to say that there exists some xy. So this means, so this statement is, you have to show, there is a little bit of steps. So xy belong to R if and only if xy belong to R op. So this is saying as same thing as xy belongs to R if and only if yx belongs to. Okay, so that is the element-wise description. You get it now? So you see, if you, this is the standard way of saying. So again, using this kind of notation, it says x rho y implies y rho x. Okay? So you see it's the and therefore y rho x also, therefore now there is a, now let's look into some examples. So let's take any set A. Immediately we have empty set, which is a subset of A cross A, and A cross A also is a subset of A cross A. Right? So both are relations. Empty set is a relation and A cross A is a relation. Which one is reflexive, which one is symmetric? Can you say now? Can you make a guess or give me reasons? Is the empty set reflexive?
Yes.
Why?
Because for all elements of your empty set, that element with the pair of that element and that element is in the empty set.
Okay, just look here. It says that empty set would be reflexive. You have to be a little slow. Reflexive if you take this for all x in A, not the empty set, x belongs to the empty set. Is this true?
No.
Unless A itself is empty. Right? If A is empty, A cross A is obviously empty. Right? If A is empty, so this is true, this can be true, the valuation of this is true if and only if A is empty. Right?
Yes.
So therefore, the empty relation is a reflexive relation if and only if it is the empty set. Now, that's why you will see me often writing things avoiding the usual for all x style. I usually write it in this way. X belongs to A implies XX belongs to R. Okay, so this is my phrasing for this thing. Why? Now you use the fact, if A is empty, this side is already false, so this statement is true. Right? So, if you take R to be empty set, then this statement is true only in the case when X, this one is false, that means A is empty. So that gives a clearer idea. Okay, so that's one thing that you will always see, that I am avoiding the use of for all and replacing it by an implication. Okay? So for me, in my language, actually I completely avoid, or for all is actually an abbreviation for an implication. Okay? So that's how I consider it. And essentially, it is used in that way. And, okay, you will see. Now for statements, as I said before, you see, reflexivity is an implication statement. So, phrased in this way, it's an implication statement. Everything, symmetry is also, and symmetry is, phrased in this way, it is an implication statement. So, implication statements, as we said as we saw from the first day, it is to be carefully taken, right? So there are something called vacuous implications and so on. Okay, so this is never, so phi is never reflexive. The empty set is never reflexive unless it is defined on the empty set itself, right? Okay. Is this symmetric? Can you tell me now? Is this symmetric?
I'd say yes.
Yes, because the empty op is also empty set. So this is always symmetric. Okay. Now, so in this way, you'll have to start finding examples. Then you'll have to find the. What can you say about A cross A? Is it reflexive? What is A cross A? So if you take R to be A cross A, so is it reflexive? Is it
Yes.
Yeah?
If you restrict it, yes.
Why? A cross, because, or what do you mean by restricted?
A cross A is the whole relation, right?
Yes.
So
on
it
A.
might,
The whole relation on A.
the whole relation on A, yes. So, okay, I'll say if, for instance, we have more than one element in A,
Yes.
then you will get instance where you have a mix. So if you have, for instance, A subscript naught and A subscript 1.
Okay, let's take an example. Suppose A
Yes.
is 0 and 1. So A cross A has 4 elements.
Yes.
0, 0, 0, 1, 1, 0, and 1, 1. Yeah?
Yes.
So, yes, now say what you are going to say. There are mixes and so on.
Okay, so the element number 2 and element number 3 from the way you've written there, then those ones would not be what's this? Yes, those would be the mix.
Good, but what I have said is, if I take any x from A, xx must be there. Is there an exception to this rule? I didn't say that R would only contain elements like xx. I have said that if I take an element x from A, then the pair xx is in there. I am not saying about other things that R may or may not contain. Is it clear?
Yes.
So then,
Okay, yes, then it becomes what's this?
yes, so it,
Symmetric. Yes.
yeah, so it becomes reflexive, right?
Yes. Sorry, reflexive. Yes.
And then, is it symmetric? Yes, because again, using one of those, the op of A cross A is A cross A itself, or if you take this, if xy is there, then yx is obviously there, so it is symmetric again. So you see, you can also draw schematic pictures. Usually, we denote A cross B like this, where A is this and with this B is this. So by this, although it's a schematic picture, so here, and the delta A or the diagonal is exactly this, right? So that is my diagonal. So what it says is a relation. If it has to be symmetric, if something over here is there, then if you take its reflection, you can think of it in these terms. If you take its reflection in this diagonal, that is also there. So that is the picture of symmetry. Okay? So it is symmetric, so the diagonal is a line of symmetry for that shape. So any general relation looks like this. So in this schematic shape, any general relation looks like this. I didn't make. Oops. So this is the diagonal. So any general relation, so I should say, I shouldn't draw this. Anything like this. Any subset, anything that you can think of, any subset of this. So what is symmetry? Symmetry means that whatever should this, it should also contain this diagonal. So it should contain this diagonal. So the symmetry means that the relation must contain all of this. Yeah. So that's, and symmetry then, this is reflexivity. This is reflexivity, this is a general relation, and this is exactly the scenario for symmetry. Okay. So, there will be others also coming. So you'll have to, so as I say, you have to make up this element-wise thing and find all these properties. And yes, finding counterexamples or examples, non-examples, it is not trivial. But one hint is, try out, although we have not proved it, but we know that there are these sets containing with 2 elements, 3 elements. I have never used the smallness anywhere over here. So use that. So think of 2 element sets, 3 element sets, and try to find out relations which satisfy one property and not the other, and try and see how much ticks can you put in this square, in this table. Yeah, how much examples can you put? That is indeed a good exercise. Okay. Any further questions? I am just tempted to tell a story, and that is the story of how one of the very celebrated theorems in topology came up. The author, when he was asked to give this talk, he was saying that as a student, he was given the problem book to read topology. And the problem book accompanied by a book of examples. But, the book of examples being very old, almost all of it was consumed by insects, these insects which nibble across books, so except for the last few pages, the pages which had all the properties listed on the columns and different spaces, list of all the spaces which were discussed in the book. But the book, several pages were eaten out, so many of them could not be read. So he started looking into this table, and he says that I saw how can I maximize the number of ticks in this table, and trying to find a space which maximizes the number of ticks in the table. Okay, so what does it mean? It means that it has the maximum number of properties listed on that, in that, or considered in that table. And that gave rise, if I had such, so that gave rise to several conditions or several relations between these properties, and that gave rise to this theorem. So you see, this is a, well, I'm not saying that this 4.1.2 would give such, but this is a good exercise to do. Whenever you encounter these notions, you should make up a table and try to see the maximum number of ticks that can be given to an example. And by that you will discover relations automatically by yourself by these. Trying to finding these examples, you will find a relation between these properties. Okay, so all right. So now let's see if any other further questions from you on week 4. Yeah? Is everyone asleep?
No, I'm good in terms of week 4. I don't know about the others.
Okay, others? Is that?
I'm good with week 4.
Yes, what is it? I couldn't hear you, Janil.
Sorry, I think I'm good with week 4. I just have questions about week 5.
Okay, all right. So let's come to week 5. So,
Okay, so with regards to week 5, understanding the axial regularity was a bit interesting, but after sitting with it for a while and looking up other explanations of it made sense. But then the idea of when a relation is well-founded, I'm kind of not 100% understanding, and then because of that, everything else doesn't 100% make sense. Yeah, so why a relation is well-founded and the definition of that.
okay. And Malatse?
No, the way you've written it down in your notes, I can sort of make out what it says, but okay, I had read from other sources as well what it means for a relation to be well-founded. So it was just trying to interpret what is written there, and I don't have a problem with the definition in terms of that one, but then the others.
Okay.
Yeah, I haven't gotten very far, except for up to the well-orderedness and yeah.
Okay. So you see what it says is how can we picture this? Another possible way to picture this would be like this. So these are two copies of A, and I shall write an element which is related to this by something like this. Okay, and it very much looks like a function, but not really, because for a function, you know, from one point you cannot go to several places. So this tells me that this is related to this. And this tells me that this is related to this, and well, it could also be related to this, and so on. So some are left out over here, and some are left out over here. So what is this doing? It is actually trying to figure out the relation in this form. Okay. So this is also another this is another facet, another picture for representing relations, trying to say that which elements are related to what. Now, what is well-foundedness? So, you take a non-empty subset. So, you take a non-empty subset. So, when do you say this relation? When do you say this relation is well-founded? Let me write it out first. So it says that whenever, so how did I write it? I said that for all subsets y of A, if y is non-empty, then what was the thing? S. Okay. Then there exists an S in Y. What is the property? The property is that whatever X you might take from Y, then XS is not in R. So what does it mean? It means that you will be, so you take any subset of Y or any subset of A. Sorry, you take any subset of A. So it's the same thing. So that's the subset Y. It is non-zero, so it has things inside. Now it says that there exists an element over here such that for all other elements, whatever you might do, there is no arrow coming to this. So there is no arrow coming to this. So how do I do that? This is not allowed. This doesn't happen. Okay? For any other place coming to this doesn't happen. So, in other words, you are for all subsets, well, obviously, I don't know, there could be things going out from this, there could be things which are related to this, but nothing is pre-related. So, shall we use this word saying, if I, so this is my S, if I say that XS, let us use this, X is R predecessor of S. Okay? So it says that there exists an element of Y for everything, there exists an element of Y which doesn't have any predecessor in it. Well, it can be the case that, let's see, it can be the case that from outside you can reach this. That I am not telling you. That is possible. But for each subset Y, you do not have anything in that set which is predecessor under that same relation to S. Everything is possibly a successor. So that means we will say X is a R predecessor and S is a, let's make it a generic note, so of Y, and Y is a R successor of X. Okay. So what I am trying to say is that this element S may have are successors in that set, but may not have, but does not have any R predecessor in that set. Okay? It becomes a little more clearer if we agree. Okay, let's look into a solid example. Natural numbers. Take its usual order. Okay? Now, take its usual order. Now, do you know this statement? If A is a subset of natural numbers, then A has the smallest element. I'm sure you have heard about this. I'm sure you have heard about this proposition. Have you not?
Yes.
So what, see, how does this two relate? So what are you saying? For all A subset of n, the moment A is empty, there exists an A from A such that for all x in A, so we usually write this in our usual way. X is not less than or equal to A, and then using the fact that the natural numbers is, the order is, using the fact of ordering, we write it in this way. Right? That's exactly this statement. This statement and this statement are exactly the same. Agreed?
Yes, makes sense.
So this is kind of therefore saying, so this says that the usual order of natural numbers is well-founded. Okay? But this is not true for even Z. The usual order is not well-founded. So that means, what do you do? How to prove this? Well, obviously, you're saying that means this statement is false. That means you have to give me a non-empty subset such that which doesn't have a smallest element. Can you do so?
So just any subset that starts with the negative infinity until in a specific number, for example 2.
Why complicate life? So, why don't you say x in Z so that x is less than or equal to 0? That's it. That's what you said. Negative infinity, I don't know what is infinity and what is negative infinity, but I know this property. X is less than or equal to 0. And why this doesn't have any smallest element? If I take any x from A, x minus 1 is still from it. Right? This basic fact tells me that, and it is smaller than x, so it doesn't have a smallest element. Done. Okay. So you see that there are relations which are, and a well-founded order relation is usually called a well-ordered. Okay. All right. Now, so essentially what is well-founded being about? Well, well-founded is just trying to say that In that relation, for any set of elements that you might take, you are going to have a kind of smallest element in that order. Is it right, if we say it in this way? So, roughly speaking, we are trying to say that every non-empty subset Y of A has a R minimal element. And what will be the definition of an R minimal element? Precisely this. That it is an element of that subset which does not have any R predecessor. That's it.
But then, Doctor, I don't know. In terms of some textbooks, minimal and minimum are easily confused.
Yeah.
Shouldn't we write better the R minimum element instead of minimum? Because
yeah, that's why I said it's minimal, because minimum is usually written when the minimal becomes unique. There can be several minimal elements, but minimum is unique, right?
And also maybe belonging to the set to the subset as well.
No, that I force. So it's when I say that it has a R minimal element, I'm saying that element belongs to that subset. Okay. So there is an R minimal element, and that is inside that set. That's what I'm trying to say. Okay? So that's the idea of well-foundedness. So see, regularity is therefore telling us that your universe of small sets, in this universe of small sets, belongs to is a relation. This is a relation on this. Okay, this is a relation on this. And it is saying that this is epsilon. This is well-founded. This is well-founded. Why? So if you take any set of sets, I don't know, so Y is any set of sets. Y is non-empty. Then there exists an X from Y such that I said S over there, S from Y, such that for any X from Y, X, S is not in, so that means X doesn't belong to S. Right? So this means X belongs to Y implies X doesn't belong to S. Right? So this is the same thing as saying either X belongs to Y or X belongs to S. Now, this is, remember, P implies Q is not P or not Q. Okay? So, this is the same thing as saying Y intersection S is empty. right? So this same thing can be written therefore equivalently as there exists an S in Y such that Y intersection S is, and this is exactly, this part is exactly a direction of regularity. So see, what are you doing therefore? The idea is, if you take any set, you will find a subset whose elements themselves are, none of them are here. The elements of this, none of them are here. Okay? So you could have another set whose some element is also over here. So you kind of see a picture like this element is common. Okay, this element is also appearing. So how do I draw it? So something like this possibly. So there could be sets like this, right? Something like this. So this element is common between this and this, and so on. But I don't know how to draw this. But there exists something which doesn't belong to it. Nothing of it belongs over here. So it has no intersection with it. So that means if you go down, if you take something over here, you take something over here, at some place this thing stops. That's the problem. At some place it stops. So essentially what regularity is giving us is a kind of an atomic structure of the universe. Why? It says that the universe therefore springs from empty, then you take its power set, then you take its... so we will see at the end of this course that this V is obtained. This V is obtained like this. It starts... let me go to another page. It starts with this being the empty set, V1 being the power set of this, which is 1. V2 is the power set of this, which is 2. But I don't stop here. I take this also. Right? I'm sorry. I take the power set only. V3 is the power set of 2. So, it's the power set of 2, it has 4 elements. V4 is the power set of 2, and so on. And so on, we carry on. And then what do we do? Well, we will see there is something called V0, which is the smallest thing, which is bigger than all of this, and it will be this union. Well, I'm just writing now. And then you carry on again. So V0 plus 1, that also can be defined. That is nothing else but this power set of this. So at stages like this, you go on taking power sets. At stages like this, and there will be many such, you go on taking all the information, you collect all the information that has been taken up so far. So you just take the union. And V turns out to be the union of all these V alphas. So this picture, this very beautiful picture, this you include over here, then you include this, and then and so on, you go on and on and on. So this picture, this atomic picture, is ensured by axiom of regularity. And as a result, you see immediately equation 91, that you cannot have a set which belongs to itself. You cannot have it. You cannot have a cycle in that chain. That means x belongs to y belongs to x, and this can be done for any finitely many things. But I didn't. Yeah. So you see, this whole fact of axiom of regularity is kind of it's giving a very conservative picture, very conservative atomic picture of the universe. Whether this is true or not, well, maybe everybody possibly have seen the video, and which I sent yesterday. Well, such things are childish to ask. You don't ask whether this is true, whether this is. It's the belief system. So if you believe in an atomic universe of sets, you have to accept the action of regularity. That's its power. That's what it does. Okay, and then there are sets which are not well-founded, epsilon well-founded. But to do that, to study them, in our set theory, there is no set which is not. Every set, our epsilons is well-founded. So if you have to take a set theory which is not well-founded, you have to reject the axiom of regularity, and such sets as I have given in 5.2.5, it is actually the domain of something called Exalian set theory or non-foundational, non-well-founded set theory. And there is also a lot of results in that. So the converse also exists. I mean to say, you have a theory which of well-founded sets, you also have a theory of non-well-founded sets. Okay? But we will be doing well-founded set theory.
Excuse me, Doctor.
Yeah.
This is a bit difficult to articulate, but it's kind of I understand that what you're saying is there's good justification for taking regularity, right? Because of the way it cleans up results like this.
The idea is I want to do counting, I want to do our usual mathematics.
Yeah. But kind of philosophically, I think mentioned it, if we look at the axioms we've looked at so far, they all looked to me, and it's just a subjective thing, but they seemed clean and they made sense, and yes, of course. And regularity just felt artificial, if that makes sense.
Yeah.
It felt like it was, it's like I understood what it was saying when I'd read it and reread it and reread it. But I guess what I'm trying to ask is, when it comes to axiomatic set theory, should we be looking at results? Should we not be maybe focusing on our axioms without results in mind so much if we're trying to build a theory that's just purely coming from our, intuitionistic basis? Does it make any sense, the question?
Yes. This is where, as we have now agreed that once we select our language and then so on and so forth, statements, its truth values are all known, we select a few axioms and start off with a theory. Okay? How are we going to select those axioms? This is exactly the question that you are asking. Now, if I have, now this is where, once I select, the next part is syntactic and it has no, what do I say, no evidence based or nothing is, but the selection, how do I do the selection? There is no choice of that. There is no rule for that. If I select some set of said statements, I'll get a theory. You can select another set of statements, you will get another theory. Well, it could be shown that whatever results I prove to be true in my theory, you can prove the same results in your theory. So we can consider our theories to be equivalent. Or we can say, we can see that whatever results I prove, whatever statements I prove to be true in my theory, you can prove also, but you can prove some more. So you will say that your theory is an extension, conservative extension of my theory, and the other way around. But there can be theorems, there can be statements which are true in my theory, and in your theory it is either not true or not provable, not decidable, and so on, and the vice versa. So in that case, these two theories are incompatible. So you see, there are a whole bunch of theories. Now the question is, what to do with which theory? Now, what to do with each theory is obviously determined by what are its statements that are proved by that theory. So what are its collection of deducibles? And it turns out that the mathematics that we are going to do, like we are going to know about numbers, we are going to know about our usual counting, we are going to think about solutions of these equations that come up from this, and hence the spaces, the solution spaces, and hence spaces that come up from this, and so on and so forth. If we have to do this theory, then it turns out that we would have to select a theory of sets which is well-founded. Otherwise, we'll stumble upon even counting business, we'll stumble upon it. No well-founded, no counting. No well-founded, no gluing. So our usual procedures will just break. So that's it. So the answer is that, well, we have selected this this well-founded theory of sets because we want to speak about our usual mathematics. And that's why I actually gave that reference in that book, that there are several other things, including facts about numbers. And that's why non-standard analysis was mentioned over there also. So, including certain facts about numbers, they are also true in non-well-founded set theory and are better explained there. Here it is explained, but it is a little more conspicuous, a little more circuitous. There it is much more simpler. So, you see, the fact that I said that non-well-founded set theory is obviously incompatible with well-founded set theory, but there is a whole bunch of results which both of them share equally. Okay, so there are some things which these two theories share, and there are some things which they don't. So Does that answer your question?
It's a very good answer to my question. Thank you. Can I just take it one step further?
Yeah.
How would you feel about me then saying there's a degree of empirical method in set theory, in the sense that we test which ones correspond to we choose our theory on the basis of a test as to which ones correspond to our notions of numbers and such?
Yes. Not only for set theory, for each and every theory, there is an empirical. There is obviously an empirical principle, and in the theory of in the area called mathematical logic. So as I was saying, the selection of axioms is often called a presentation of a theory. So you are presenting the theory. So the moment you give me the axioms, you have given me the theory. So the selection of the axioms is a presentation of the theory. And it can be shown that different presentations, so theory in general is not defined by the axioms. Axioms define a presentation of a theory, and there can be several presentations which give rise to the same theory, as I was saying, right? So the question is, which presentation shall I choose? For instance, there are theorems which say that the piano arithmetic is I'm forgetting it. I think yes, the piano arithmetic is not first order reducible. So what does it mean? It means that the statements that this amidst any statement that or any presentation of the theory of piano arithmetic, you cannot have a presentation involving only first order sentences. And what does first order sentences mean? Involving sentences, so axioms are sentences which doesn't involve quantifiers over subsets. You only say it in terms of variables. So it says that the piano arithmetic is not first order reducible, first order presentable. Now look here. So this is a theorem in mathematical logic. Okay, there are objects of study are theories themselves. Okay, so you see our object of study has also become different. Now what I am saying in that discourse, I am saying a particular theory doesn't have a first order presentation. So it automatically tells you that if you have to take a presentation, if you have to select a presentation, at least one of your axioms have to be second order or higher. Okay, so apart from, so which one of them are you going to choose? Well, the ones that suit you best. So you can take several presentations. So you see, you can go to a party using a traditional dress, using a formal dress, using another whatever dress and so on. I'm not that expert, but if you can list different kinds of dress. So presentation is almost like that, but it's still the same Ben, right, going to the party. So if you say Ben is the theory, then the presentations are your different dresses. Okay, so whichever you can choose, that's upon you. That's upon you to decide which one shall be presented. But obviously there is a choice, there is an empirical feature in the choice of these presentations, and In that part there is no mathematics. Mathematics only starts after you have chosen your logic and your presentation of axioms. From there mathematics starts. And there is no more any empirical or any further thing. Yeah? Does that make it clear?
Very conceptually helpful. Thank you.
Okay. Now if we see on the axiom of infinity, that 5.3.1, you see now axiom of infinity tells us that there is a small set, and therefore there are several small sets and so on and so forth. 5.3.2, it does the usual facts about natural numbers. It is the smallest inductive set. It is well ordered, and it has two variations of the principle of induction. So that's there, and then we have the piano arithmetic there, and so which is what we were speaking of. 5.3.4 is a useful and a very, very strong feature about functions. So every function can be factorized as a surjective function followed by an injective function. Now what is the idea behind? So if you have a function, so what is the picture? The picture is as we usually draw. If this is a function, then you have everything going to some place. Maybe many things can go to a single place, right? There could be others and so on, and some left over here, left outs. Okay? So these are the left outs, but nothing is left out over here. So now what do? Well, these are the elements which have a pre-image. So you take this subset. Okay, so this is your range of f. Okay. Now what is this? Well, this is your range of f, and how do you define? Well, the function changed. The moment you take, instead of b, you take the range of f, the function changes. The rule doesn't, but the function changes. Remember, the function is a triplet. It is given by the domain, the codomain, and the rule. The moment you change one of them, the function changes. So the rule might be the same, you just change the codomain, your function is, so the new function that I have drawn with this blue, that is a surjective function. And if you take any subset, you can think, so if T is a subset of B, there is automatically a function from here to B. How? Well, it is usually called the inclusion function, denoted by iota. What does it do? It takes x to x. Doesn't do anything else. Okay? So you see, obviously this is an injective function. So you can see this one breaking up as the range of f, and then this are there any? Yes. Any other? Yes. I could have taken this. So I could have taken also this T and its inclusion there. Sorry, but then if I take this, Is it going to be true? Let's see. So this part takes only this. Nothing is said about this over here. So I miss this information. So I cannot take any subset of this. For any other factorization, I have to take something more. So it has to be larger. Okay? So then you see, once I take this bigger thing, I have all the information in this factorization left over. So this is another factorization. There can be several others. But you see, this is the smallest. So the range for any other factorization, you will have a unique image over here. Unique map. And what is that map? This is actually telling you for any other t has to be, which gives this factorization, t has to be bigger than range of. So that's that map telling you. So you see, this is a very, very typical feature of a function. It is called the factorization by surjection and injection, and the unique part of it, and that's what this is about. If you keep this picture in mind, it might help you to prove this. Then 5.3.5 is, remember we spoke about in the earlier in section 4 about the reflexive closure, which is the smallest reflexive relation containing a given relation. We spoke about the symmetric closure of R. We spoke about the antisymmetric hull of R. But we never spoke about the transitive closure. And the reason is that the transitive closure involves natural numbers. That's why unless we have natural numbers in our system, we cannot speak about it. So that's how we come to this 5.3.5. Possibly you have already seen, yes, no, not yet, later on. Okay. So this is Rn. So what are we doing? We are taking R, then we are taking R composed R, then R composed R, and so on, and then taking their unions. So you are taking R, union R composed R, union R composed R, and so on. All these unions we are taking. And that turns out to be the containing R from its definition, and that is the smallest. So what is your smallest? Remember, your transitivity comes from, so R is transitive. This is transitive. The definition is saying R composed R is a subset of R. Okay. So after some work, you should be able to see that if X, I'm writing in that language, this language which we did, okay, this kind of a language, it is usually written as if X row Y and Y row Z, then X row Z. So something like this. No, it's exactly this. Okay. So what are you doing? Well, you are taking first something which is related. So if you had an XY, so if now it's a little bit difficult. So what am I trying to do? I'm trying to figure out, this one is a little difficult to figure out in that box type. So if you take an XY, if you can find a common, so you will go from here and then you go from here. Okay, so x, and if there is a z, which is x is an r predecessor of z, and z is an r predecessor of y. The moment you have it, you are going to club this. That's in xy, and transitivity would have to force it here. So if it is not, then you have to include this. So include this. So you have to take this. But now there is another problem. What happens if there is a third step? If there is a third step. So if there is something here, so you had two such things like this, right? And then if what happens here? Then, because this also came from a third such step, so this is possibly some such thing like this. Okay, so you can see, therefore this one can be seen as coming from all of these processes. So you have to take the next step, and then this continues. So you have to take all of, and that's exactly what is due. So how do you define? Remember, this dot business which worked in our school days have to be thrown out. It doesn't say anything. So what is it? There is a sequential definition. How is it? The first stage, you take R. The second stage, what is it? You take R and compose it with R. Sorry, this one. So it is S0 composed R. Third stage, this is S2. Sorry, S2 is S1 composed R. So you see, so that gives you your general formula. Sn is Sn minus 1 composed R. So you see that gives your generic formula to create this meaning, right? Who tells you that there is a, that's where natural numbers come in. Okay? Whenever you have, so you take the collection of all natural numbers for which this set Sn is defined. S0 is defined. Yes. If Sn is defined, then Sn plus 1 is defined. Yes, by this rule. Therefore, your induction principle says for every natural number n, you can define the set Sn. See, you defined only for finite steps. You defined at the start, and this is often called the recursive definition or the recursive step. You defined at the next step. What am I going to do? Given a step, how do I go to the next step? That's what. So that's the recursion you're doing. And who guarantees that therefore you have for all natural numbers? That comes from the principle of induction. That's where induction tells you that therefore there is a function from natural numbers into sets, which assigns to each natural numbers the set Sn that you have taken. Okay? So that is often called, therefore, the definition by recursion or recursive definition. Right? So that defines this, and then a similar procedure. You define T0 is S0, and Tn is, you are going to take these joints. So what is T1? It is S0 union S1, right? So what do you do? How do you define this? So this is Sn union Tn minus 1. Okay, so that's the recursive step. Okay, So that's the recursion. Now you have, so what you have done is you have defined all these partial sums. And now it's the usual series-like picture. So you have all these sets, T0, so you have this set, Tn. And you can take its union. That is your R. So this is the complete formal description of this R. What we simply write in usual mathematics by this line. But observe, while this is very intuitive, it has so much things to say. And unless we actually ensure these, which were now ensured by these axioms, we cannot make such statements. Okay? All right. Now the next thing to prove is this R is here. You'll have to use the equations in section 3. And then you will show that this is the smallest transitive relation on A containing R. And then you can combine with the your previous answers to get the smallest. Remember, the smallest equivalence relation containing R, what is it? Well, it is a relation which contains R, which is symmetric, transitive, reflexive, and if any other equivalence relation which contains R, then this one will be a subset of that. So as simple as this. Okay, so the same story that we are doing. And the last one is typical, a very, very atypical argument. And I leave it to you. If you have seen the video, you would have seen the Cantor's diagonal argument over there, what Cantor was trying to do. Writing up all the real numbers in a big table as decimal expansions, and then he got hold of a number which cannot ever appear in that. And that's how it proved. The idea is exactly the same. Over here. But you prove much more. You prove that you take any small set A and you look into its power set, you can never get hold of a surjective function. So essentially what it is trying to say, there doesn't exist any surjective function. Come back to this factorization which I told you a few moments back. Where is it? Here. So if you take this function, if you take any function f, from this factorization there is this range which is the smallest, and that gives exactly, so this is a surjective function, right? This is a surjective function, and this is an injective function. Okay? So this is an injective function. So that's what it is telling us. So therefore, in particular, if we take f like this, fx is the singleton x, that is injective. Yes, and what is this range? The range is the subsets of all singletons. So this is telling me that this function, which is coming from this factorization, is not only injective but it's bijective. So I can think of A So there is a copy of the set A already sitting inside the set of subsets of A. And the copy, what is the copy? See, bijections are nothing else but relabeling. It's like a dictionary. What X is in this, if A and B are bijective, what X, well, X, the dictionary says X is same as X prime in B. X in A is same as X prime in B. Y in A is same as Y prime in B, and so on. So it's a dictionary. So if you hit upon some element, say Z prime in B, you know its meaning, its corresponding word over here, Z. If you sit back and think, it is nothing else but saying that roughly speaking, if there is a bijection between A and B, roughly speaking it means that A has as many elements as there are in B. So injective kind of is telling me, if there is an injection from A to B, it is telling me B has at least as many elements as there are in A. So when you say that there is no surjective function, it is actually telling us, therefore, that A is actually sitting inside. So a copy of it is sitting inside the power set, and in no way is this set equivalent. So there are many, many more subsets of A than there are elements of it. This is exactly what it is saying. For any small set A, there are many more subsets than there are elements of the set. Okay? So you see, counting, we have not started till yet, but it is slowly coming up, right? Through this calculus. So, well, okay, we will see next time. That's what I have to say in this section 5. Now, I leave it to you for your queries, doubts, and so on. Yes? I didn't think I sang a lullaby that made all of you sleep.
We're awake. It's actually getting a lot more interesting, but it's hard.
Yeah, hard, as I said. Yes, hard because nothing is hard. Things become hard because we don't see it actually. That's why. The reason is, the more you get into this habit of looking at it from this point of view, these will get so hard. I disagree. The actual word is, you're unfamiliar with the methods. So the more familiar you get, you'll see it becoming very simple. But you see, the ideas are very, very fascinating, and it can be implemented here. Next. Anything more? Or should we call it a day?
Can call it a day.
Okay. Before we, Xander, you agreed to join us, right?
Yes, Doctor.
So could we, myself and Malatse, we meet on Fridays from 10 to 12, right, Malatse?
10 to 12.
Is it not 10 to 12 or anything else?
No, it's 10 to 12.
Okay.
Or maybe, yes, 10 to 12.
Okay. So then we can join, Xander will join us at the same place.
All right.
Okay. All right. So then we meet again on Friday. Okay, thank you. Keep well and good night.
Thank you very much, Doctor. Enjoy your evening.
No.
Thanks.
Thanks very much.
Thank you. Bye.
Thank you.
Goodbye, everyone.
Bye.